Hello everyone. In this session we are going to discuss about Krushkal's algorithm. In the previous session we discussed about spanning trees and we looked at the idea of minimum spanning tree and the algorithms that are used to generate minimum spanning trees. So in this session we are going to look at one such algorithm to understand how to generate a minimum spanning tree for a given graph. So the objective of this session is to understand the Krushkal algorithm, the basic steps of Krushkal's algorithm, and we will have to understand it with an example. By taking a graph, we will understand what this algorithm does to generate a minimum spanning tree, and we will have to look at some of the internal procedures used in this algorithm, and it's a very popular approach called union find approach to check the connectivity and cycle forming. And finally we will have to implement this algorithm using a programming language, and the reference is given below, so you can go through this reference for more details on this algorithm. So let's have a quick recap of minimum spanning tree. So a minimum, we know what a spanning tree is. Spanning tree is a subset of a graph such that all the vertices are connected with least possible number of edges. So out of these spanning trees we need to select one spanning tree whose cost is minimum. So it's a spanning tree and it is defined for a weighted graph, and it has the minimum cost across all the spanning trees derived for the given weighted graph. And we also looked at an example, so let's look at the same example again. So this is the example. So we have a graph with with 4 vertices and 5 edges, and the weights are defined here. So this is 1 and its weight is 2, 3, 4, 5. So in this graph we can generate one spanning tree. So we can include these 3 edges, and the cost of this particular graph is 4 plus 5 plus 2. So this is 11, and we can generate one more spanning tree. So this is the one, and the cost of this particular graph is 4 plus 1 plus 2, which is 7. So as you can see, this is the one with the minimum cost, and you can enumerate all the spanning trees for this particular graph and then find that this is the one with least possible cost. So obviously this is the minimum spanning tree. But how do you do it for any graph? So for this graph you can do it pretty easily because it's a simple graph. It has only 4 vertices and 5 edges, so you can enumerate all the spanning trees, calculate their cost, and then find the one with the minimum cost. But that is not the general solution for any graph. It's a very tedious solution. If you have a graph with tens of vertices and hundreds of edges, it's very difficult to enumerate all those spanning trees and calculate their costs. So obviously that is not very good. That's not an elegant solution. So what is the solution then? So you have an approach, and that approach, one such approach is Krushkal's algorithm. So let's look at this algorithm. So Krushkal's algorithm is a greedy algorithm. So when we say greedy, any greedy approach always finds the best option among all the available options. So it chooses the best. So when you're talking about minimum thing, so it finds the one with the minimum weight. When you want to maximize something, so it always finds the one with the highest value among all the available ones. This algorithm also uses a greedy approach. So we will understand that how exactly it uses that greedy approach. Before that, let's look at the sequence of steps performed in this particular algorithm. The first step is to remove all the loops and parallel edges. So it is assumed that students are familiar with loops and parallel edges, otherwise the example will make the loops and parallel edges clear. A loop is a self edge. So if a vertex is connected to itself via an edge, that is called a loop. A parallel edge is parallel edges are the ones which are, even if 2 vertices have more than one edge between them, they are called parallel edges. So we need to remove all these additional edges and loops as part of generating the spanning tree. That is the first step. The second step is we need to put all the edges in the ascending order of all the edges have to be sorted according to their weights. All the edges have to be sorted in ascending order according to their weights. That means the least weighted edge comes first and the highest weighted edge comes last. And the next step is to pick the edge with the least weight. So every time, because we are generating a minimum spanning tree, that means we need to keep adding edges. So we need to add minimum possible number of edges to the tree such that all the vertices are connected. So which edges have to be chosen? So every time we choose the one with the least weight. That's why it is greedy approach. So we choose the one with the least weight from the unvisited edges. If an edge is visited and added to the MST, the minimum spanning tree, we don't have to consider it because it is already added. So we always look at the unvisited edges and pick the one with the least weight and we add it to the MST. We need to ensure that it does not form a cycle because we are generating a tree. What is the basic property of a tree? The basic property is that it should not contain any cycles. So we need to ensure that this particular tree does not have any cycles. So when we add an edge, we need to ensure that. So how do we ensure that? We will look at that also while going through this presentation. So let us understand all these steps with an example. So this is a general graph given. So given we have 6 vertices and we have several edges between them. So let's first look at these things. So this is a loop. As you can see, this is E is connected to itself via an edge. So this is a loop. This is a self edge. So C is also connected. And these are parallel edges. So A, B are connected with 2 edges. So one is with weight 4 and one is with weight 5. And D, E are also connected with 2 edges. One is with weight 8 and the other is also with 8. So what is the first step of this algorithm? Remove all the loops and parallel edges. So we have to remove this parallel edge and this loop and this loop. So both the loops are removed and parallel edges are removed. The basic question is which parallel edges have to be removed and which one has to be kept. We need to have only one edge between any pair of vertices. So we need to remove all the additional edges. So which one should we keep? Obviously, we can intuitively also we can say that we need to remove higher weighted edges if the weights of those parallel edges are different. In this case, we have 4 and 5. So we remove the one with 5. It is since it increases the cost. If you have the edges with the same weight, in this case you can keep one of those edges and you can remove all the others. So you can keep any of those edges. You can keep either this or that. It doesn't make any difference. So we have removed all the loops and parallel edges. So we have this graph. So this is the first step is completed. Let's go to the next step. What is the next step? We need to sort the edges according to their weights. So we have 10 edges here. So each edge has a weight. So in this case, AD is the one with the least weight, followed by BE, followed by BD, followed by AB, AF, etc. So all the 10 edges are ordered according to their weight. So the second step is also done. The third step, the most important step. So we need to pick an unvisited edge because we are generating the MST. So there is no MST now. A minimum spanning tree is not yet generated. It is null. So we need to generate. So how do you generate? You need to keep adding the edges. So we need to pick an unvisited edge and add it and ensure that it does not form a cycle. So that is the most important thing. So how do you do it? So let us first pick the one with the least weight. So this is a greedy approach. So let's pick this one. So AD is picked. So let us add it. So this is visited. Now let's pick the second one, which is BE. So that is obviously it doesn't form cycle either. So we have AD here, we have BE here, and let's have the third one. So this is also visited. So both are added to the MST, and the best one among all the unvisited ones is this one, BD, with the weight 3. So let us add that also. So this is also visited. So now let's take the next one, which is AB with weight 4, right? AB. So can we add this? So what happens if you add AB? So if you add AB, a cycle will be formed. See, A, B, D, A, A. This cycle will be formed. So this violates the very basic property of the tree. So this creates a cycle. So a tree does not contain any cycle. So obviously it should not be added. You should reject that. Okay. So you should reject it. So this is not added. So it will be discarded. Okay, so AB, the edge AB will be discarded. So the next one is AF. So this is the unvisited one. So obviously AF, it doesn't form any cycle, so it is added. And the next one is BC. So that is also added. So you have, how many edges are there? 1, 2, 3, 4, 5. Since you have 6 vertices, you need to have n-1 edges in your tree. So the tree is formed with AF, BE, AD, BC and BD, and the total cost of the minimum spanning tree is 1 plus 2 plus 3 plus 5 plus 6, which is 17. So this is the algorithm you have. So when do you stop this algorithm? So obviously a tree with n vertices will have n-1 edges. So in this case, as soon as you reach n-1 edges in your minimum spanning tree, you can stop it. That is a very simple approach. So what happens if you continue? If you don't stop and continue, for example, in this case, if you keep continuing, what happens? CD, you may consider this, but what happens if you add this? A cycle will be formed. So obviously you will reject it, you will discard it. Likewise DE, if you add any edge, any other edge, all the edges that are not considered, that are not visited, if you consider them, cycles will be formed. So obviously you don't need to consider them. But the basic question here is, how do you detect cycle algorithmically? In this case, you can see that, because since you are manually working it out, you can understand that adding AB will create a cycle, adding CD will create a cycle here. Programmatically check. How do you instruct the computer to check for a cycle? So that is where you have a specific approach used in this particular algorithm. So how do you detect if adding an edge forms a cycle or not? So the answer to this question is find union approach. So this is a very popular approach used, and it uses set theory concepts. So let's look at what the basic idea of this particular approach, and let's work it out for the same graph. So the first thing is initialization. In this approach, we need to initialize, we need to divide all the vertices into different sets, and each set consists of only one vertex. So having initially, for example, if you have 5 vertices A, B, C, D, E, you have 5 sets. Set 1 will have A, set 2 will have B, set 3 will have C, set 4 and 5 will have D and E respectively. And the next step is find. So when you add a new edge to the MST, when you pick a new edge, you need to check the belongingness of each of those vertices. If they belong to 2 different vertices, then, so that is where the union step comes, you need to add that edge and merge these sets. If the vertices of the edge being added are from the same set, that means it causes a cycle, so you'll have to discard it, you'll have to reject it. So we need to repeat this find union steps every time when you pick an edge and try to add it to the MST. So let's see how it exactly works. So this is our graph, the same graph which we used for generating the minimum spanning tree, and these are the edges with their weights. So the first one is we pick, so this is what the initialization step. So we initialized all the vertices here. So we picked AD, obviously it's fine. So because that's the first thing. So now we need to check the belongingness. A belongs to set A and D belongs to set D. So both are different sets. So as per the algorithm, we can add it. So let's add it to the minimum spanning tree. and we union it. So we have AD, so A and D are unioned, so you have AD, B, C, E, F. So these are the 5 different sets now. Initially we had 6, now we have only 5. Now let's choose BE. AD is done. Now let's choose BE. Pick BE. So B belongs to set B and E belongs to set E. So since both are different sets, we can add it. So let's add it and union. So AD, because this is union here in the first step, now we have B and E unioned. So you have BE, CF. So we have 4 sets now. Let's now pick BD. Okay, let's check the belongingness of B and D. B belongs to set BE, D belongs to set AD. Both are different sets. So let's add the edge and union. So you have A, B, D, E, you have set C and set F. Now let's choose AB. So pick AB. So let's check the belongingness. A belongs to both A and B, both belong to the same set, A, B, D, E. So that means they do not belong to different sets, they belong to the same set. So adding this particular edge will create a cycle. So that's what we have seen while generating the minimum spanning tree also. So we will have to discard this particular edge, and obviously we don't have any union to be performed here. So we are still left with only 3 sets, A, B, D, E, C and F. So let's choose AF now. Now A belongs to A, B, D, E, F belongs to F. So these are 2 different sets. So we add it and we do a union. So A, B, D, E, F, and we have set C. Now let's choose BC. So B belongs to A, B, D, E, F, and C belongs to set C. Both are different sets. So we add it and we do a union. So A, B, C, D, E, F. So now we have only 1 set. So obviously any new edge added will belong to the vertices of any new edge added will have their belongingness in this set itself. So they belong to the same set. Obviously their inclusion will create a cycle. So we will have to stop the algorithm here. So what is the other way to find when to stop the algorithm? Obviously if we have only 1 step, if you are using find union approach to form a cycle, and if you have only 1 set, that means the minimum spanning tree is formed. So this is the observation. Can we stop the algorithm if we are left with only 1 set? Obviously yes. So we can stop the algorithm if you have only 1 set at the end of the find union algorithm. Now let's look at the complexity thing. So what is the time complexity of Krushkal's algorithm? Intuitively, the most important step to sort the edges according to their weights. So if you have E edges, the best algorithm, if you use a heap sort or med sort, any algorithm, any best sorting algorithm, then you'll have a time complexity of order of E log E, assuming that it has V vertices and E edges. So E log E. Checking whether adding an edge forms a cycle or not is not pretty difficult. The find union thing is very simple one, because it's at least it's not it's not costlier than this sorting approach. So obviously you can ignore that while calculating the time complexities. Its total time complexity can be amortized as order of E log E for a complete graph, because if you talk about a complete graph, that is the maximum graph that you can create, maximum connectivity graph you can create for any set of vertices. So in that case, number of edges for a complete graph is V into V minus 2. So if you substitute it, you will have the time complexity of, so if E is equal to V square V into V minus 1 by 2, so you will have a complexity of order of V square log V. So this is the time complexity of Krushkal's algorithm. So you can use either this or that. So we will have to look at the implementation part, and that implementation of this algorithm is given here. So it's written using C programming, and it has taken one example graph. So you can extend it, so you can put your own graph, or you can scan the adjacency matrix of the graph from the console and then use this approach. So either way you can test this algorithm and try with different examples. So the summary part is that finding minimum spanning tree. If you use Krushkal's algorithm, then finding minimum spanning tree uses greedy approach because it always chooses the least weighted edge, and the steps are to remove loops and parallel edges, sort the edges in ascending order of their weights, and then add the least unvisited edge, ensuring that it does not form a cycle. And the approach used to find whether adding an edge forms a cycle or not is find union approach, and it is based on set theory. And the time complexity of this algorithm is order of E log E or order of V square log V. So concluding this particular session with a quiz. So you have a quiz hosted here, the location is given here, so you can open this quiz and answer your questions after going through this presentation. And all the questions assume that the graphs are undirected unless specified, and if there is more than one possible option available, choose the best among all the available options. Thank you.